Myself, Dr. Sudha, Assistant Professor, Department of Mathematics, Government Science College, Autonomous, Bengaluru. In this session, we are going to study vector differential calculus. In that, scalar and vector fields. Let us begin with the introduction. So let us define what is a scalar. A physical quantity which has only magnitude is known as a scalar. Some of the examples are time, mass, density, pressure, volume, energy, etc. Now let us define what is a vector. A physical quantity which has both magnitude and direction. Examples: force, velocity, acceleration, displacement, momentum, etc. Let us define what is a scalar point function. So for that, let us consider any region R in space. Let P be any point in the region R and phi of P be a scalar which corresponds to every point P in the region R by any law or rule. Then phi is a scalar point function over the region R. So if you consider a region R and a point P, to every point P, we can associate a scalar phi of P by any rule or law. Such a function phi is known as scalar point function over the region R. So now let us look into a few examples. If P is equal to x comma y, an ordered pair in two dimensions, then phi of P given by the rule x square plus y square is a scalar point function and it forms a scalar field in two dimensions. Suppose if P is x comma y comma z, a triplet, it is a point in space, then phi of P is given by the rule x square plus y square plus z square is a scalar point function and it forms a scalar field in three dimensions. Now let us see the definition of vector point function. Let R be any region in space. Suppose P is any point in the region R, then one can associate a unit vector f of P to every point in P. So if you consider a region R and a point P, we can associate a unit vector f of P to every point P. Here f is called the vector point function in the region R. Also the points in the region R together with the values f of P will form a vector field over R. Now let us look into a few examples of vector point function. If P is x comma y, then f is equal to f of P and that is equal to xi plus yj, where I and j are the unit vectors along the x-axis and the y-axis, is a vector point function and it forms a vector field or the source field in two dimensions, and we can represent a source field as you can see in this diagram. Here the vectors are away from the origin. If P is equal to x comma y, once again an ordered pair, it is a point in two dimensions, then f is equal to f of P equal to minus x into I minus y into j is also a vector point function and it forms a vector field, or it is also known as a sinc field in two dimensions. In diagram, we can represent a sinc field like this. Here you can see that the vectors are approaching the origin. Similarly, we can define a vector point function in three dimensions, that is f is equal to xi plus yj plus zk, where x, y and z is represented by the point P. It is also a vector point function and it forms a source field in three dimensions. So in diagram, we can represent a source field in three dimensions like this. Now let us define an important operator which is known as the vector differential operator. A vector differential operator, it is denoted by the symbol del or nabla. Usually we call this as del, and it is defined as del is equal to I into dou by dou x plus j into dou by dou y plus k into dou by dou z. Even though it looks like a vector, it is not a vector, but it is a vector differential operator. It can also be represented as dou by dou x into I plus dou by dou y into j plus dou by dou z into k. That is, we can write the unit vectors before the operators, or you can write them after the operators. And this vector differential operator will possess all the properties of ordinary vectors. So what all laws or properties of ordinary vectors are there, they are applicable to this vector differential operator also. In the next session, we are going to study how this operator acts on a scalar point function, also on a vector point function. Thank you.